So what do all of the phenomena that we just witnessed have in common? Well, if you're thinking rotation, then you'd be right, but we'd like to be a little more specific than that. We've already studied force as it results in translational motion, objects moving from one point to another. However, that understanding wouldn't allow us to explain what we just witnessed, so we need a new concept, torque, the rotational analog of force.
Even if you don't recognize the concept of torque, your body does. Have you ever considered why, when you open a door, you automatically reach for the side of the door opposite the hinges? Why, when you twist a wrench, your fingers are automatically on the side opposite the end of the screw? Why the pedals on a bike are so far removed from the axle? Well, it all has to do with torque. Torque is mathematically defined as R cross F, or R times F times the sine of theta, where R is the distance between the fulcrum of rotation and the location where the force is being applied, F is the force vector itself, and theta is the angle between the two vectors. So, I've prepared some objects here to help quantify torque. First, I have a rod with some distances pre-marked, 5, 10, and 15 inches, respectively. I also have two weights here, a 2-pound weight and a 3-pound weight. In many cases, what you want to do is not just produce torque in an object, but balance torque in an object, essentially maintain equilibrium. If that's the case, then much like when net force on an object is 0, you want the net torque on an object to be 0. So, if I took my 2-pound weight and placed it at the 15-inch mark, then where would I have to place my 3-pound weight on the opposite side to maintain equilibrium in this rod? Well, let's quantify it. We have 0 to 15, so 15 inches multiplied by 2 pounds is going to be 30 inch-pounds. Now, if that's equal to the torque on this side, then we have 30 inch-pounds is equal to 3 pounds times some distance x. So 30 divided by 3 is going to be 10 inches. So that means, theoretically, if I were to place my 3-pound weight at the 10-inch mark and my 2-pound weight at the 15-inch mark, then this rod should stay in equilibrium. So let's give it a shot. And as we can see, it does stay in equilibrium. So that's how torque works.
Let's look at an example similar to the demonstration we just watched. For simplicity's sake, let's say the beam is exactly 1 meter long, and that the fulcrum is exactly in the center, so half a meter from the end of the beam. Now, there's a 5 Newton force acting on the beam, 0.3 meters from the fulcrum, and there's a second force of unknown strength also acting on the beam on the opposite side, which, as you may recall, is exactly half a meter from the fulcrum because it's at the end of the beam. Now, it's our job to determine the force X required to keep the beam in equilibrium if it weighs 2 kilograms. So stop and think for a moment. Is the weight of the beam relevant to solving the problem in this scenario? Well, it actually isn't, and here's why. If you reduce the force of mass of the beam to a single point force, then that force is going to be directly on top of the fulcrum, and it's going to have strength, 20 newtons. However, the distance between that force and the fulcrum is going to be 0, and as such, the torque due to that force is also going to be 0, so it won't factor into any torque calculations we may do. So here's all the information we need to solve the problem. And we also have all the information we need to calculate the torque due to the force on the left, so let's go ahead and do that. When you run the numbers, the torque on the left will come out to 1.5 Newton meters. We also said that the beam is in equilibrium. This means the net torque on the beam is going to be 0. So essentially, the torque on the left has to be equal to the torque on the right. Therefore, the torque on the right is also going to be 1.5 Newton meters. We can use this to calculate the force X required to keep the beam in equilibrium. When you run the numbers, this comes out to exactly 3 newtons. Here's another problem. Let's take a look. So here we have a beam with a single applied force acting at some angle theta relative to the beam. Now it's our job to find that angle theta to keep the beam in equilibrium. So here are some things you need to consider when solving the problem. First, where is the center of mass of the beam and how far is it from the fulcrum? Second, what is the equivalent force at that point due to gravity? And third, once you find the torque around the fulcrum due to the weight of the beam, what can you set it equal to? Try this problem for yourself and bring your solution to class tomorrow, along with any questions you may have.